Okay, it seems that we are live on YouTube, or are we? Yes? Oh, very good.
Are we using the right link? It seems strange not to see people.
Yeah, no, I did not yet let them come in. Just a
Oh,
second.
I see. That's why. Okay.
Yeah. Uh, but this time it's going to be much less strict with the muting. The last time was my first time, so I muted everyone to reduce possible.
Zina has a very special treatment. Thank you so much.
Well, last time Carlo complained a lot. To be fair.
Mm, okay. Let's wait until 4:07.
Which would be 11:07. Okay.
Oh, nice. So even when people can unmute themselves, they do not unmute and make a noise. Because I don't know if you were in the last KISS seminar, but I did not let people to unmute themselves. I just was afraid there would be too much noise. But yes, I'm positively impressed.
Well, 5 years in, we should be good at this now, right?
Yes, we're all COVID veterans. So it's 11:07 for you.
Yes.
So, hello everyone. Good morning, Doreen.
Good morning.
Good afternoon to our European viewers. And I guess good night to our Japanese viewers and Australian viewers. Welcome to the second KISS seminar of 2025. My name is Ofek Ben-Giat. Today we are going to hear Doreen Fraser. Doreen is a professor in the University of Waterloo. And she's doing philosophy of physics and history thereof. She will talk to us today about superluminal signaling and when it can and cannot happen. You are right, I should start the recording. Oh, thank you, Western University.
Great. Thank you very much for having me. I'm looking forward.
Just a second, sorry.
Okay.
Yeah. Okay, so I started the recording. We are also live on YouTube, by the way.
Okay, excellent.
Good.
Can I get started?
Yes, Doreen.
Okay.
Yes, you can get started.
Thank you very much for inviting me. I'm really looking forward to a good discussion about this topic. So I've pulled threads for this talk from a larger collaborative project I've been doing for the past couple of years with Maria Papiorgio, who is in Vienna. But of course, the standard disclaimer applies that she may not agree with everything I'm about to say. Okay, so since this is a multidisciplinary group, I want to start by being really clear about the question I'm asking and my perspective on this topic, because I would expect that different people are going to have different perspectives and are going to think different questions are interesting. So I'm a philosopher of quantum field theory, and I'm primarily interested in foundations of quantum field theory, questions surrounding superluminal signaling. So this means that my focus is on prohibitions on superluminal signaling that are physically attributable to relativity theory. So of course, there are lots of other physical reasons why we may not be able to signal, such as there are walls blocking our signals, but this is not really the circumstance I'm interested in. There's a received view, of course, that superluminal signaling is prohibited in relativistic theories and permitted in non-relativistic theories. And I'm not going to be doing anything to challenge this received view today. So the question I want to focus on is, how do relativistic quantum theories prohibit superluminal signaling? And so, of course, then I have to define what I mean by superluminal signaling. And I'm going to adopt a restricted definition for the purposes of this talk. So I'm going to be interested in space-like separated regions. So primarily focusing on Minkowski space, although many of the, especially later in the talk, many of the accounts I'm going to talk about are going to be generalizable to globally hyperbolic space-time backgrounds. And the main restriction is going to be to local non-selective measurements that are performed in one region, and the condition will be that they don't affect expectation values for local observables in a space-like separated region. So this restriction to non-selective measurements is admittedly artificial. It's not intended to be any sort of fundamental restriction. And of course, it's motivated by thinking about non-relativistic quantum mechanics, where we think that we might have a good handle on restrictions on superluminal signaling if we can find attention to non-selective measurements. So the question I'm going to focus on here is superluminal signaling by non-selective measurements already physically prohibited in non-relativistic quantum theories? This would be surprising given the received view, but it's a possibility. Not surprisingly, I already advertised my answer is going to be no. Then you might think that hybrids of non-relativistic and relativistic quantum theories might prohibit superluminal signaling. But I'm going to push and give us reasons to think that we have to go all the way to my third option, which is that superluminal signaling by non-selective measurements is only prohibited in relativistic quantum field theory, combined with a relativistic local measurement theory for quantum field theory. Okay, so this, given the way I've set up this definition of superluminal signaling, I'm focusing on non-selective measurements. So you might think that that's obvious already, because in order to determine whether there's superluminal signaling, you have to have some representation of non-selective measurements. You need local measurements in order to model signaling. So you might think that's obvious, but of course there's reasons to think that it's not obvious. So that's what I'm going to be talking about. So here's the plan. So I'm going to start off with Galilean quantum field theory, in which it's unambiguously clear that superluminal signaling is permitted. And then I'm going to focus most of the talk on superluminal signaling and the question of whether it's prohibited if we take on board relativistic quantum field theory and we combine that with a non-relativistic quantum measurement theory. And my answer there is going to be no. And I'm going to give you two reasons, two kinds of counterexamples, which show that superluminal signaling can occur in this context. So one is Sorkin type impossible measurement scenarios. Another one's drawn from philosophy of quantum field theory. So I'll talk about that one in a little bit more detail. This is actually most of the talk, but to give you a concrete idea of what I mean when I talk about a relativistic quantum measurement theory, here's quickly two examples that I'll talk about a little bit more at the end. So there's a detector-based measurement theory that's recently been proposed, and then there's also the FV measurement framework for algebraic quantum field theory, which are relativistic versions of measurement theory. Then conclusions. Okay, so Galilean quantum field theory is a theory in which you have quantum fields, but they are in Galilean space-time with Galilean causal structure, rather than Minkowski space-time. So this is not a naturally occurring theory. It was a theory that was proposed after the main axiomatizations of quantum field theory had been proposed, Whiteman and algebraic ones. And the purpose of it was to get clear on what was new about relativistic quantum field theory by comparing it to another theory in which you have an infinite number of degrees of freedom. Okay, so you can think of this if you're know about Newton-Cartan theory. It's a little bit like that. It's an imaginary theory which is filling out the possible theory space in a way when we're looking back from a theory we have and trying to figure out how it relates to our past theories. So why start here rather than standard non-relativistic quantum mechanics? Well, this framework, as I just said, was intended for comparison with quantum field theory, so it's kind of useful. For our purposes, it's helpful because the Galilean space-time structure and causal structure is made explicit. So this means that if you take as a causal principle that if two in a quantum theory, that if two regions of space-time are causally disjoint, then the observables associated with these regions have to mutually commute. Then this gives you different axioms for Galilean quantum field theory and Minkowski quantum field theory. So we're familiar with Minkowski quantum field theory, where you have space-like separated regions commuting. In Galilean quantum field theory, you're only going to have commutation between regions that at equal times have non-zero spatial separation. Okay. So the thought here is, of course, you're flattening the light cones, and so you can see here a clear difference between Minkowski and Galilean quantum field theory. So there's an obvious question. So if we want to prohibit superluminal signaling for non-selective measurements, is it sufficient to add microcausality to standard non-relativistic quantum mechanics? So this would be an example of a theory I would consider a hybrid of non-relativistic and relativistic quantum theory, because it's combining standard non-relativistic quantum mechanics with this additional assumption that we're adding on, motivated by wanting to get closer to relativistic quantum theory. Okay, so I'm going to pursue this question. I'm going to note here, though, that There's lots of other differences between Galilean quantum field theory and Minkowski quantum field theory that may turn out to be relevant. So this is genuinely a question about whether this is going to work. So we fairly quickly realized that the answer is no. So here's a little bit of an information theoretic way of thinking about it. One of the original papers in which the no cloning theorem is proved is a paper by Dennis Deeks. And the motivation for the theorem is consideration of a proposal in which you have an EPR set up, and if you are allowed to clone to clone the system that you receive, then you're going to be able to signal superluminally. So this leads to the recognition that you're going to need more than just microcausality to rule out to rule out superluminal signaling in non-relativistic quantum mechanics. So here Deeks is pointing to dynamics. So the linear character of quantum mechanical evolution laws is also being something that's going to come in. So it can't just be microcausality by itself. Okay, so keep adding then. So what about microcausality plus unitary evolution in non-relativistic quantum mechanics? Is that sufficient? The answer is no. Here, I'm just going to gloss over this point because I want to get to talking about the role that relativistic measurement theory applies here. But you're also going to need to consider the relativistic dynamics. So quickly, a way to think about this is that if you want to rule out superluminal signaling in, say, classical relativistic field theories, then that's going to hinge on having dynamical evolution, deterministic evolution of the fields propagating within the light cone structure. You're going to be assuming that the causal light cone structure you get from your field equations is going to line up with the light cone structure from the space-time. And then that's going to mean that if your fields are propagating subluminally, then the idea is that that's going to help to guarantee at least that you're not able to signal using those subluminally propagating fields. Okay, so there's some references on what this looks like when you spell out these arguments. I'm going to move on to the next question. Okay, so now we're going to grant ourselves, oh, sorry, I see there's a hand.
Doreen,
Go ahead.
what is an example? I cannot think of a way of having a microcausality in the sense that I've understood that together with non-relativistic dynamics. Are there examples? I just can't imagine how this happened, because the commutator between two different fields into different space-time regions is whether they're dynamically connected or not. How does this?
Okay, I went over that quickly. So yes, that's an excellent question. I'm assuming that this is a consistent sort of combination. So, right. So I'm going to give up on the reason for thinking that in Galilean quantum field theory, we had this causal principle saying that you have commutation at equal times for non-zero space-like separation. Now I'm moving to standard non-relativistic quantum mechanics, and I'm adding the condition in by hand that algebras of observables associated with space-like separated regions are commuting.
Yeah, but the algebra observer has to satisfy the equation of motion. If the equation of motion says that fields are depending on one another space-like region, they cannot non-commute. So do we have an example of that? Or just we talking, do we have an example of a theory where there is a microcausality, but the dynamics is non-relativistic? I can't, it seems to me it's impossible. Do we have a counter example of that? Okay,
so I'm on the same page as you here. So I'm going to push on. So I'm going to push to so if I'm understanding your question, it's, is this proposal even consistent, right? That I'm making here. Like, do we have any examples of non-relativistic quantum theories where you take into account
it
field.
seems to be a contradiction. What is? I mean, I understand that Dennis Dix is thinking about something which violate non-linearity of the evolution, but that's going out from quantum mechanics altogether. Within quantum mechanics, what would be a theory that? Just drop this question if you is there one? Can you point one to a theory that has these properties? This is strangely seems self-contradicting properties.
Right. Okay. So, is there a theory that has the properties of microcausality plus unitary non-relativistic dynamics? Right. That's the question.
If I give the fields on a time slice, the equation of motion tell me what are the fields at other time slices. And if the equation of motions are non-relativistics, there's no way to avoid that they don't commute even at a space exploration.
Right. Okay. So so I'm gonna say at this point that this is where I'm going, right? So where I'm going is I'm trying to push us to think about what happens in a fully relativistic framework, right? So what I'm thinking about here is cases in which you think about non-relativistic quantum mechanics, and then because you do want to have no superluminal signaling in the context of non-relativistic quantum mechanics, you take on board as an additional requirement over and above non-relativistic quantum mechanics that you're also going to insist that when you're modeling a system, two systems using non-relativistic quantum mechanics, that you're going to have to make it so that so that there's commutation between
simulated, but we don't know by what.
Okay. All right, so I'm going to push on because I'm agreeing with you, Carlo, here, I think. So let me push on. Okay, so I think the question I want to focus on here is the question of what happens in the context where we allow ourselves all of quantum field theory. So the dynamics of quantum field theory, as well as microcausality in a fully consistent relativistic theoretical framework. Can we add non-relativistic quantum measurement theory on top of that and prohibit superluminal signaling in that context? And my answer there is going to be no. And I'm going to give you two counterexamples where we have this framework and we see that we still have superluminal signaling. Okay, so the first example is an example that's originally due to Sorkin, a possible measurements example, and then has more recently been dealt with in a slightly different way. So this is the more recent version by Borston, Jum, and Kells. So the setup here is that you have O1 and O3 are regions that are space-like separated. And so you have Alice performing a non-selective measurement operation or a local unitary operation within O1, and then Bob is within region O3. And then you also have an observer in region O2, Charlie, and they are they're going to perform a non-selective measurement operation. So region O2 is in the overlaps with the causal past of region O3 and with the causal future of O1. And what Sorkin and others show is that when you model the system that you're measuring with quantum field theory, you include microcausality as an assumption. You are taking quantum measurement theory from non-relativistic quantum mechanics in the form of Luder's state update rule for non-selective measurement. You are also assuming that you have unitary time evolution. Then you are going to be you show that Bob is going to be able to identify the operation that Alice performs. Okay. So right. So what I'm trying to argue here is that you need to go to quantum. You need to go to relativistic quantum measurement theory in order to model in order to prohibit superluminal signaling. So there are, of course, logically possible ways to respond to this kind of scenario in which you retain quantum measurement theory from non-relativistic quantum mechanics. And instead, what you do is you exclude any operations that permit superluminal signaling in this kind of way on the grounds that they're unphysical. So you exclude those operations. Okay, so while that's a logically possible response, it's not the kind of response that answers the question that I'm interested in here, the foundational one, about how relativistic theories prohibit superluminal signaling. So a question I would ask here is, why are these operations being excluded? What is the physical reason for that? And then that would be the physically illuminating answer to how do relativistic quantum theories prohibit superluminal signaling. Okay, so I should say that this is actually not a criticism of this view, because this is how, or this approach, because this is how this approach is presented by the people who advocate for it. So it's called an ad hoc approach, which in philosophy, ad hoc is usually an insult, but the idea here is that this is a useful way of proceeding in this context where in an ad hoc way, all you're doing is you're ruling out the operations that permit superluminal signaling, so then you get back to having no superluminal signaling. But there's lots of reasons why that's a useful thing to do that are pointed out by these authors. So I wanted to make it clear that this is not to say that because this approach does not answer my question, that it's not a worthwhile thing to do. It is for different reasons, but not for this kind of reason. Okay. So the other thing I wanted to say here is there's a bit of an indication that you're going to suspect you might need to move to relativistic quantum measurement theory anyway. It's that in order to figure out how to apply non-relativistic quantum measurement theory in this scenario, you're going to need to identify a temporal order for the regions, which of course you can do, and you can do it in a covariant way. That's not the issue. But the fact that you need to add more structure, which is structure for non-relativistic space-time, to have an absolute, not absolute, but to identify some temporal ordering relation that would allow you to apply the measurement theory from non-relativistic quantum mechanics is an indication that you're importing assumptions from non-relativistic space-time context that you might want to get rid of when you move to the full relativistic quantum context. Okay, so the second counterexample that I want to talk about, which is another case in which you have full quantum field theory, you pair it with non-relativistic quantum measurement theory, and you find that you still have superluminal signaling, is an example that comes from the philosophy of quantum field theory. So the context for this example is what I've called Hogg-Hassler algebraic quantum field theory. So this is a traditional way of axiomatizing algebraic quantum field theory. It goes back to the 1960s, to Hogg and Hassler. I point that out because more recent approaches to algebraic quantum field theory are not within this particular axiomatic context. So we're taking on board all of those axioms. And we're going to go back to bipartite measurement scenarios for space-like separated regions. And so the results I'm relying on here from a paper by Reda and Valente, and they also draw on other results by Summers as well, those two. Okay, so the observation here is that if we have non-relativistic quantum mechanics, we add what I'm calling the microcausality assumption, but all I mean by that is that we assume that the algebras of observables associated with space-like regions have we assume that they commute. So we add that in as an extra assumption on top of non-relativistic quantum mechanics. And then we treat all of this using quantum measurement theory. Then no superluminal signaling between space-like separated regions. The two that we've identified, because this is bipartite, unlike the previous scenario. You're going to have no superluminal signaling guaranteed by the Krauss representation theorem. So as long as you have Krauss operators in those two algebras, then everything's going to work out nicely. So these authors point out that if you then move to quantum field theory, so of course, Hogg-Kastler algebraic quantum field theory includes microcausality as a standard axiom. And then you treat this, we'll use quantum measurement theory in this context. So you're going to need a slight generalization here, which is the analogous. So the second footnote. So what this means is that you're going to generalize to considering normal operations that are not mapping between sets of bounded operators on your Hilbert space, but between any algebras. Then you're going to find that this analogous no superluminal signaling result would not hold in this context because you no longer have the Krauss representation theorem being applicable, because you have type 3 von Neumann algebras, which don't have any finite projections in them. Okay, so this is an example in which you see that you can have superluminal signaling if you put together these ingredients. So Redeye and Valente have a proposal to restore the no superluminal signaling result from non-relativistic quantum mechanics in a slightly generalized form. And so it turns out that if you add to the standard Hogg-Kastler axioms for algebraic quantum field theory, the condition that the split property holds, so the split property holds is that you assume, excuse me, that there exists a type 1 factor in between the algebras for the two regions, so that the prime indicates the commutant. So if you assume that you have some type 1 factor, which is the case in which you have bounded set of bounded operators on a Hilbert space, so this is like bringing in something back from non-relativistic quantum mechanics, then it turns out that you do have a no superluminal signaling result, which is very similar to what you have in the case of non-relativistic quantum mechanics. Furthermore, it turns out this seems to be a physically reasonable thing to assume, assuming that you have double cone diamond regions that are strictly space-like separated. Okay, so again, I think of this as being a logically possible response to superluminal signaling in this context of algebraic quantum field theory plus non-relativistic quantum measurement theory. But I have the same kinds of questions that come up because I'm interested in how relativistic quantum theories prohibit superluminal signaling. Adding the split condition then makes me wonder why the split condition, what physical role is this condition playing in ruling out superluminal signaling? Unless it's physically motivated, it seems like it's not really answering my question. It's another way of adding a constraint, which has the effect of ruling out superluminal signaling in this special kind of circumstance where this kind of condition holds, but it doesn't really answer my sort of foundational question about what it is about relativistic quantum theories that prohibit superluminal signaling. Okay, so to wrap up, so what I've tried to push us to is to what I would think of as the kind of fully relativistic context of relativistic quantum field theory plus relativistic local measurement theory for quantum field theory, and then you do have superluminal signaling being ruled out. The history here is very interesting. The dominant tradition in quantum field theory has been asymptotic scattering theory as the basis for the measurement theory. But there have been attempts to formulate local space-time regions measurement theory for quantum field theory since before quantum electrodynamics. Marie and I have a paper about this. So here are two examples, which I'm just giving you as examples. I'm not going to say much about them, but clearly these are not the only two ways you can think about how you might devise a local measurement theory for quantum field theory, but these are two well-developed examples. So the first example is detector-based measurement theory. And the idea of this example is, sorry, this approach to measurement theory is that you are proceeding along the lines of inspired by the paradigm case of Unruh de Witt detectors. So you use quantum field theory to model the system, and then you use non-relativistic quantum mechanics to model the detector. Then you apply Luder's rule to the detector, do a projective measurement, and then you get information about your quantum field theory system. So importantly here, this gives you new state update rules for the QFT system, which are different from the state update rules you have for non-relativistic quantum mechanics. So this is, I think, a sort of easy way to see that this is a new, different relativistic measurement theory for QFT. The second thing I want to point out is that the result that you can rule out superluminal signaling is limited, right? So what you can do in this framework is you can show that in regimes in which you would expect your detector model to be a valid model, then you can do the calculations using standard techniques from quantum field theory, and you can show that superluminal signaling is ruled out for all practical purposes, which means to some suitably high order in perturbation theory. So you are going to get signaling, but you can show that it's negligible within this model. So this is, to me, actually quite important because often the advantages of this model are made out to be practical, but I think this is a real foundational advantage to this model. And it's the kind of thing we would expect following the logic I've been trying to follow through here, that if we combine elements of non-relativistic quantum mechanics with quantum field theory, then we are going to get signaling. We are going to get non-relativistic effects, and that's precisely the attitude that's taken in this kind of approach. Okay, the second example is a way of, is a proposal for a measurement framework by Fuster and Verk, entirely within algebraic quantum field theory. So in this framework, you use algebraic quantum field theory to model both the system and the probe. And again, to emphasize, this is relativistic quantum measurement theory because you derive new state update rules. By analogy to the steps you take in non-relativistic quantum mechanics to derive not just Luder's rule, but the more general instruments and measurement schemes, et cetera, that you find in quantum measurement theory. You derive new state update rules for quantum field theory in this framework. And then you can show that you can rule out superluminal signaling for non-selective measurements, such as in the Sorkin type scenarios. Okay, so to wrap up then, the question that I've been focusing on is how do relativistic quantum theories prohibit superluminal signaling? So I've argued that we have reasons that even for the case of non-selective measurements, that we need to consider a relativistic theory of quantum field theory plus a local measurement theory for quantum field theory specifically to capture all of the physical principles that rule out superluminal signaling. And then I've suggested that there's elements that combine to contribute to rule out superluminal signaling in this framework, either for all practical purposes, as in the one example, or in principle, as in the other example. And those principles are microcausality, relativistic dynamics, relativistic local measurement theory. So one of the features of the logical situation here is it's logically possible to rule out superluminal signaling in what I've been calling hybrid quantum theory, so some kind of combination of non-relativistic quantum theory plus relativistic elements by introducing additional conditions. But I've tried to suggest that these additional conditions that you need to introduce in those contexts are not physically illuminating. All right, thank you. So I look forward to discussion.
Thank you, Doreen. I see there are already questions. So, Western University, please.
Robert, do you want to go first? I just asked a question before.
Oh,
Yeah, sure. Okay, so thank you, Doreen. That was a very nice overview of the state of the art in superluminal signaling and measurement in quantum field theory. I just want to make a small compliment to what you were saying. So it seems that you were missing the latest results in the context of what you called what was the setting of Sorkin and the situation. Yeah, thanks for going back.
Yeah.
with the slides. Yes, exactly. That one, and also so you were saying that this was reanalyzed recently by Joe Boston Kels, and then that the proposal was to say, okay, so maybe we can do some measurements in the sense of the non-relativistic scheme. So there has been progress recently. In fact, so I've been able to show that you can measure all field operators. So operators like phi of x, or more generally, any operator that's a sum of creation and annihilation operator can be measured in a way that does not induce superluminal signaling. Basically, by using the non-relativistic scheme, but there are some subtleties, some mathematical subtleties. You have to consider some limits, but if you take that into account, you can do that. So I just wanted to say that.
Thank you for that, because yes, so your paper is one I have to study more carefully, and so one of the really exciting things about this area is how active it is right now, but that also means that I'm finding it hard to keep up with all of the new work that's being done. So thank you for that. For that addition. So let me go back to here. So I think maybe this is more appropriate to what you're talking about, right? So
Yes.
Following up on this proposal and then showing that that what you can that you can so one worry you might have here is that you don't that if you're ruling out any operation that can permit superluminal signaling, then you're ruling out too much, right? And there are operations that you want to represent that as in which in this framework that have to be ruled out in this framework, right? So what you're saying is that you can show that you can that in this that you can actually represent the operations that you would physically want to represent. So it's not like you're being left with too few observables or operations.
So the point in particular is that it's a relatively large class of observables that you can measure this way, because you have these field operators, but you can also measure functions of them. So I just wanted to mention that. So
maybe I can follow up and ask you if you have an answer to my why question then.
Yeah. I guess one reason why I mean, previous kind of no-go results have been so convincing is that so to go around that, it's basically okay. So in the non-relativistic situation, the way you would deal with this is you have your observer, you make a spectral decomposition, and then you construct quantum operations from the spectral decomposition. And the problem is that if you construct this quantum operation by binning the values that you want to measure, so in this case, the the measurement values are real numbers. So you have all the real line as the spectrum of your operator. And if you bin that, then as Jupp and Kels have shown, this leads to superluminal signaling. So you have to use a continuous version. You have to measure the whole the value of your observable finely, infinitely finely, so to speak. And you have to use certain limits to do that, and then it works. So that's kind of in a nutshell. By the way, if you want to know more about this, in 1 week, I'm going to give a talk about this in the loop quantum gravity seminar on Tuesday, just in case.
Okay, great.
Thanks.
Thank you.
Yeah, Doreen, can you go down to the slide, the one you put before with the picture? Yeah, no, the one with you have a relativistic temporal in red. Yeah, perfect. Thank you. Let me I look at this from with the eyes of physicists. So let me help to see where we are. I found this very interesting and very challenging. In fact, the first time I learned about this sorting idea is from you. And at the beginning, I was very surprised. I said, "Oh God, what's going on here?" It challenged me a lot. Say, do I have something wrong in my mind here? Let me tell you what was my sequence of thought, and tell me if I'm wrong. I thought that so my understanding is that quantum field theory as it is, and let me then come back on what we mean by what it is. Of course, it does not allow faster than light signaling. If we would build devices and send it to the Pentagon and become super rich, and I would make Italy the superpower of the world.
So then don't send it to the Pentagon.
Right, yeah. So already there's a contradiction. I will send it to the Italian army that would.
No, it's Gracias.
I will send it to the Russians. Okay. Okay, so stop it.
The aliens.
So let me go ahead. So, but then I came back to this and I said, wait a minute, there is a mistake here. If I now at the light of my all this discussion and blah blah blah, there's a clear mistake here, and it's obvious what the mistake is, because quantum mechanics tell us that I can do the non-selective measurement, which is a fancy name for doing a projection in a special cases of projection, the collapse, only if there is a temporal ordering, or 1 before 2 because of 3. But there isn't here. I mean, there's no temporal ordering. So definitely, if I want to know what guys of 1 measure and what guys of 3 measure, whatever happens in O2, what I should not do is to collapse of 1, collapse of 2, collapse of 3. Namely, I should not do a non-selective measurement 1, then a selective measurement of 2, and then a selective measurement of 3, because that's not the temporal ordering between the 2. So therefore, the point seems to me that Sorkin example tells me that picking arbitrary foliation and treating it as it was non-relativistic quantum mechanics in this simple, naive manner, it's wrong. So I would work the other way around. And then the question seems to me you're asking is good. So what is the right thing to do in these cases? Are we on the same page or not?
Yes. So I agree that there's no superluminal signaling in the world that we know of, right? So this is all a question about how we set up our representation so that we're reflecting that fact, right? So so I'm on the same page with you. And in fact, I think this is what the part I went over quickly was the part about how you think about relativistic dynamics, right? And so I think so there's a lot there as well, which is, I think, what you were suggesting when you talked about thinking about picking one preferred foliation of Cauchy surfaces or whatever, right? And then thinking about being able to apply non-relativistic quantum mechanics after you've picked out a preferred foliation, right? So I think what you can see in this example is, as you were saying, that even if you think you're doing that in a Lorentz covariant way because you have microcausality, so it's not going to matter which foliation you pick, you're going to get the same expectation values when you do the calculation. That's not the relevant piece, right? The question is, like, how do you represent both the dynamics in a relativistic way and the measurement theory too, is the part I was trying to stress here, in a relativistic way.
I guess
so I think that what I said just agree with what you said?
I guess where we might find not on exactly the same ground is that it seems to me that given any concrete situation, if you tell me not a non-selective measurement, if you tell me what happens physically in O1, what happens physically in O2, what happens physically in O3, you give me the problem. I, as a physicist, can tell you what the outcome of the measurement, and there is no. And the way I have to do it, I know what to do every time there is a confusion about measurement, which is simply include the detector of the system, right? It's what we do every time there's an ambiguity. So if instead of O2 treating it as a non-selective measurement, you treat it as an ancilla, and then we go to a final slide where everything commute, and just we read the pointer variables of whatever observable we have the prediction of quantum theory. They're univocal, there's no doubt. So it seems to me that quantum theory, as it is, if we don't do mistakes like this one, give us all the order. Would you agree with that, or would you say no? Quantum theory is incomplete unless we add something more specifically about local measurements.
So I think you need to say something more specifically about local measurements, partly because actually what's more interesting than what I've talked about is selective measurements, right? So as you're saying, really what we're interested in is what happens when you condition on a particular outcome and not consider non-selective measurements, right? So then this is what I've been thinking about lately. I think this is really actually quite interesting and different when you think about how it gets represented in the relativistic measurement theories. Because of course you don't want superluminal signaling in the sense maybe of superluminal influence, right? In the case of selective measurements. So I think that's something that's interesting to look at when you have a relativistic measurement theory.
Okay, thank you.
Lizia Novak.
Hi, Doreen. Thank you for the seminar. Please,
Hi.
you mentioned the Galilean quantum field theories. Reminds me, because I know, of course, Galilean theories in cosmology and gravity theories. What is the connection to?
Good question. I'm not actually sure whether there is a direct connection. So you were thinking, is this are you thinking about the Newton-Cartan example that I talked about? Or are you thinking about something else?
Yes, this, yeah.
Yeah, so I don't think there's any direct connection. I just think of them as playing a similar kind of role, right? Because it's natural once you get a new theory to try and fill in all the space of possible theories between your new theory and your old theory to get a sense of what has really changed, right? So it's kind of it's artificial, right? Nobody would ever use this. As I said, it's not a naturally occurring theory, right? So nobody would ever really use it for anything, but it is very informative to be able to contrast this theory with Minkowski QFT and to think about the differences. Yeah, so I'm not sure I don't see that there is a like physical or like logical connection between Galilean QFT and Newton Cartan theory, but I think of them as playing the same kind of like philosophical or foundational role.
Okay, thank you. And I have one remark concerning it was not mentioned during your talk that you was talking about relativistic quantum field theories and that how they forbid superluminal signaling. But I mean, the point is that alone, relativistic theories does not forbid superluminal signaling. And it's a question on quantum field theories, which are dictating through the no-go theorems that the superluminal signaling is forbidden. So yeah, this is my remark. Just
okay, thank you.
Thank you.
Do we have another question from Western?
Yeah, I do. Thanks, Doreen. That was a great talk. And it's just a clarifying question because I'm not as up to speed with this literature as you are. So when you were discussing the Fuster-Verge framework, you said that something to the effect that additional AQFT principles are needed to roll out the superluminal signaling, if I got this right. And
Yes, that's,
wondering what those principles are, and in particular, in what way they're kind of like better than the split property. I understand that this, I guess, is no longer the Hack-Kastler context, but yeah, could you say like a bit more on this? And because you seem to be very kind of you seem to be kind of uneasy about the split property. So I'm wondering, how do you feel about these additional principles and what they are?
Okay, good. So what I mean by additional principles here is, so here I'm thinking specifically about non-selective measurements, and I'm thinking about the Sorkin kind of scenario, which is what this paper is referring to. So the additional principles are actually not additional in this case. They're some of the axioms, right? So what I had particularly in mind in this case is the time slice property, which is the axiom which represents the dynamics in this particular version of algebraic quantum field theory. And so this is maybe more to the point that the relativistic dynamics is also playing an important role here in ruling out superluminal signaling. And so that's what I had in mind there. So it's actually not, that's probably a bad way of putting it, but so you do, I mean, you do need some other assumptions as well, which is interesting. Maybe this is interesting. So you need what's known as the causal factorization assumption as well here. So that's, I mean, so that's common to a bunch of different frameworks, including the detector-based measurement theory as well. So that's the assumption that that if you are doing successive measurements, that the sort of local scattering operators that you have for those are going to factorize. So that's an example of another assumption that you need there.
I see. So then the answer to the question why is really, well, it just follows from the kind of proper formulation or better formulation.
Right, exactly. Yeah.
Awesome. Thank you.
Hi, Doreen. That was great. I just have a question or comment, or what are your thoughts on you talked about selective and non-selective operations, right? And so I guess my question is, so typically, if you just think about the ordinary Luther's rule, right? I do an experiment that's a non-selective operation, but there's various possible outcomes, and if I specialize to one outcome, that's a selective operation. But I don't think there's any operation that's going to pick one of those outcomes and make it happen with certainty, right? So the non-selective operation is a mixture of selection ones with the Born rule probabilities. Now, it seems to me, and tell me if it's right or not, if I think of things in relativistic quantum field theory and think of the things the same way, like if all the operations I can do, are non-selective operations, which might be mixtures of selective ones, but I can't choose which selective one I'm going to do. And if someone in space-like separation can't find out which one of those outcomes was the outcome faster than light, then pretty much everything goes through. Like in effect, as like there's a sense in which if I think that only one of the experimental outcomes is the one that happens, so I'm not of many worlds or something like that. There's a sense what happened was a selective one, but because I don't have control over which one happens, for someone with space-like separation, it is in effect the non-selective one, which is the mixture of all those selective ones.
Right.
Right? Yeah.
So, and so I think this is of course the line that's popular in thinking about this in thinking from a more philosophical perspective, right? So then that's another reason for thinking about non-selective measurements as being the ones you really care about if you care about superluminal signaling in this kind of operational sense that I was putting it forward, right? So another way, so a related idea is that that you don't need to really worry about selective measurements because the selection piece is merely conceptual. So this is something that various people have endorsed, but that comes up in Rob Clifton and Hans Halvorson's work on algebraic quantum field theory. Yeah, so I think you have to change the, like, if you're thinking about selective measurements, then you're going to, as I think you're suggesting, have to start thinking about superluminal influences. If you want to say causal influences, that's fine with me too. But rather than setting up things in the very operational way that I set them up here.
Yeah, so we're going to say the context of my remark. So I wasn't thinking of the selection as being purely conceptual. I think that would be, you know, like if I have something like an Everettian view, I can imagine that, okay, what, you know, all of these things sort of happen, and you know, we might mentally pick one out. I always think about dynamical collapse theories, right? Like if you have a dynamical collapse theory, one of those outcomes is the one that happens, right? So it's not purely conceptual. There's a physical matter of fact about which one happened, right? But we don't have control over which one's going to happen. So the actual operation, in effect, is this mixture of the selective ones and someone in space-like separation. Since they don't know the outcome, you know, as long as they don't know the outcome, and our operation, you know, with one outcome, you know. Yeah, basically the operation is going to be one of these selective operations with these probabilities, and the mixture of those is a non-selective one. As long as as there's no, you know, at space-like separation, there's no effect. You know, the person can't know which one it is at space-like separation, and also the dynamics don't care which one it is. Then I don't think
so I think that's important too, right?
And I don't think there's any worry about either signaling or causal influence.
Okay, good. So that's actually similar to the way that this detector-based measurement theory works, actually. So so the thought is that if you do a selective, so you do the measurement on the detector and then you infer properties of the QFT system from the detector. The idea is that if you do a selective measurement, then in the causal future of where you do, as the observer, the measurement on the detector, then you use the selective state update rule, right? This is related to the idea that then you can, like, then that's going to be where you could signal and that you could find out, and the dynamics would know in some sense where the what the outcome was. But then in the rest of the space-time, you use the non-selective update for that reason that you just said, right? Because there's no way of influencing the systems in the rest of the space-time.
Yeah.
So yeah, so I see what you're just saying as something, as an idea that's been picked up in this relativistic measurement theory as well.
Yeah, and the people who've worked on relativistic dynamical collapse theories have, of course, had to deal with these things and, you know, make sure that there's no signaling or you know, action and distance in these theories. Yeah.
Carlo again from Western.
Mm-hmm.
I want to understand something that has confused me. In the sorting example, again, the use, thank you. The use of non-selective measurement, it's needed, or if O2 just give a very naive and simple projection, you also get the effect. Is that correct? You also get the violation of.
Oh, so if you do a selective measurement, then yes, right. So the idea of restricting to non-selective measurements is they're thought to be harmless, right? Whereas you could think that if you do a projective measurement, then with projective selective measurement, then it might not be surprising to you, depending on your interpretation of quantum theory, right? That there would be an effect. So it's not necessary in that way, but the idea is that this is supposed to be a case in which people would naively think that there would be no signaling, and then they get surprised when there's signaling.
Oh, I see. So you're saying if O2 does a projection, there is clearly a violation.
Well, then people might not be surprised,
and
right?
people will not be surprised.
Like, think of Wayne. Would Wayne be surprised if there's a projective measurement in O2?
I see. But still, it's just a. I see. Okay, thank you. That's an answer.
Please, Nick.
Yeah, hi, Doreen.
Hi, Nick.
Thanks. Hi. So yeah, I really enjoyed that. I was just going to make one quick comment, but first, and then a question. So the comment was just about Carlo's the comment before last about whether these things are these things not being temporally ordered. I mean, I know Sorkin doesn't refer to Helwig and Krauss in that paper, but that's how I kind of think of his argument. I mean, according to them, I think. I take what he's doing there as a sort of counterexample to their sort of consistency proof of that this all works out okay if you do this. So I think there's and I think then you can take what Carlo was saying as showing what's kind of wrong with their reasoning there about how it sort of fails.
Sorry, you're saying what's wrong with Helwig and Krauss's reasoning?
Yeah.
That's right. Yeah. So there's no so you might think the problem is, it's just not. We used a state update rule that's not Lorentz covariant. Use Helwig and Krauss's proposal for a Lorentz covariant state update rule, you still get the same problem, right?
Yeah. And that, and in their paper, they try to show that it works out consistently, and this sort of shows the lacuna in that reasoning, I think. So
right. I agree. Yeah.
The question was just, does any of this look different if you use different locality conditions from microcausality, like the spectrum condition, or primitive causality, or local primitive causality, and yeah.
Yes, it does. Well, so by the time you get down here, one of the things that happens is that this version of AQFT is a version that's designed for well, in this case, you need globally hyperbolic spacetimes, fixed globally then you consider like collections of such, but for this case, to make it simple, fixed globally hyperbolic spacetimes. In that kind of framework, I was talking about the time slice property, right? Which is which a version of it is local primitive causality. So that way of setting up the dynamics is going to turn out to be crucial in this particular framework for ruling out superluminal signaling in this kind of in the Sorkin kind of case, for example, right? So so this is a version of because you want to be able to generalize to globally hyperbolic spacetimes, you don't want to have any assumptions about a preferred vacuum state or anything like that built into this version. But you can still see how the dynamics is operating. Does that help?
Right. So, okay, yeah, maybe you said that before and I didn't, and it sort of went past me. Okay, so you do need so in the fuse to virtue, using something that's logically sort of stronger and more general than microcausality.
Oh, sorry. And so then you have microcausality as well, right? So you have both. So my
Does the
takeaway here.
microcausality follow from the time slice property?
No, they're independent.
Oh, okay.
Yeah.
Okay.
So one's dynamics and one's kind of a kinematical condition.
Okay. Okay. Thank you.
Okay. Seems there are no questions anymore. Am I right? Okay, so let's thank Doreen again.
Great. Thank you, everyone.
So next month there is not going to be a KISS seminar because there is the KISS conference in Vienna. Yeah, I guess we'll see most of you there. Then the month after that, in May, Francesca Vidotto is going to talk. Yes. Hi, Francesca. So yeah, have a nice evening or day if you're in Canada.
Thank you, Doreen.
Thanks, everyone.
Ciao.